Hi, everyone. My name is Merate Barakat. I'm an associate professor at the Department of Architecture. Speaking of imposter syndrome, I'm an architect, so everything I've been doing is from that perspective. My work looks at soundscape, psychoacoustics, and what that means in design, and that means that I had to tap into computational methods, pervasive methods, and some sort of augmented ways of capturing sound and using it in design. So I'm just going to go through some projects that I've looked at, and I usually collaborate with a lot of people. So in this project, we were looking at, as an architect, when you go to a site, you need to document the site. You need to document what that is, but there's no way to document sound. It's something that is temporal. It is something that it depends on the designer's perception of it, and it changes from time to time. And so in the morning, if you're going during work, or if at night you're going if it's in the middle of the city, and so we were looking at how do we document something like this for designers? And the issue is not about what the technology itself, it's more of for designers, how can they use the technology that's out there to document it? So it's not the resolution of what that means, and it also doesn't mean that the sound needs to be at high quality. So I worked with a colleague from Music and Technology in the UK, where we compared different types of recording systems. Some of them were in the water, some of them were like 7,000-pound microphones, and a 360 GoPro. And for his work, obviously, this 360 GoPro was not the best resolution, but for an architect that is trying to document the site and trying to, I'm not left-handed, and I winged my dominant hand, so. Thank you. And so we were trying to figure out a way to do this on a laptop by someone that is not used to using programming, someone that is not able or willing to learn these things, but they want to document it for different reasons. And so with a simple iPad that has a LiDAR technology and a 360 GoPro, we managed to come up with a way to document different sites as sort of a gaming with a 360 binaural sort of aspect. We worked on campus, so that video that Luke is scanning right there, that is the campus in Bristol. We also were commissioned by a local architect in a city at the bottom, at the southwest of England, where it is a city that was thriving until Brexit, and then because of fisher rights, their culture is changing because they can no longer do some fishing. So they brought us in as part of a Brixham Trust Fund to document the city and try to find different ways of designing new ways of community planning. A different project that was a feasibility study that was funded by the UKRI was the idea for computational designers to maintain their empathy in the design. So when you start working on a project, you talk to the client, or you have some ideas, and then when you start working on the technical stuff, you forget, like 2 weeks, 3 weeks, 2 months down the road, because of trying to work out the technical issues, you forget the initial intent. And so the idea was to come up with a sounding board and a think aloud protocol. So with using natural language processing, we were thinking, okay, how do designers start documenting over time what their intent was, and what is the visualization of that, and how can they communicate with these issues. We tested it out in a product design office in London, and the biggest issue was the Think Aloud protocol. Even though we talk to ourselves in our homes in the dark rooms, but when you're in an open space office, it's very difficult to encourage that communication because it usually comes with a lot of cussing and swearing and just frustration. And so that took some time, and we were trying to look around and think around that issue, is how do you maintain that? But also when you're working on a project, you're not alone on the project. So how can you maintain the intent of all the designers from their meetings, their pre-working meetings, and while they are working, and each one is working. Some are working on the fabrication, some are working on the digital computation, and some were working on the ideation. And so another project which I've worked with a colleague who looks at the Vchotimus School of Design. It is Russian, 1960s Russian sort of pedagogy, thinking of how to teach new designers the idea of composition, and visual composition. So when we think of composition as musicians, we think of that as, composing a piece of music. So designing as for visual designers, we know that there are some aspects of what makes a good composition: balance, symmetry, all these things. But Vchotimus came up with sort of a matrix and a set of sort of examples to teach the students. Obviously, this was manual, and it has been, my colleague, Dr. Levov, has been running first year, which is 230 students every year, and has been doing that manually. And so we thought, what is the difference between them learning it by hand and if you run the same sort of exercise on the computer? And because we have all this data, we are now working on, instead of just having the students run their examples and then give it to someone to grade for them, how can we train a machine to actually indicate, and so then the student, while they're doing it, they know that they are too far from a good composition, or getting closer, or getting some sort of feedback, essentially. And there we go. So this part where, as an architect, the buildings we know are starting to get smarter, we're getting these sensors, but the idea is, how can this building have a dialogue with its users? So my colleague who has been working with me, he's a phenomenologist, does not do any technology, but he has the sense of how do we be? How are we being in the space? How do we be as a community? How are we on our own if we're one or two people? So, and at the same time, I was trying to figure out how people navigate a space collectively in response to sound. And so we set up a sort of an installation in a crypt in Bristol, where it's a simple set of sensors, and the system figures out, okay, if you have one person, then there is a ideal position. The user does not know that, but as they're moving, their speakers are moving from pink noise to an actual music composition. If there's two people, then the system starts encouraging them to find the positions that will help them both work together. And if there's three or more, then they start navigating the space. And so the idea was, for my perspective, I was trying to figure out how people will navigate the space. And in his example, he was trying to figure out the phenomenological response to these changing oral senses. And so this is the music that we use is my colleague's friends. He let us borrow it. After 2 days of the exhibition, it was a bit nauseating, but it's a beautiful piece. So one of the things that we didn't realize, that if if there was a group of people that knew each other, they started negotiating, but then the ones that didn't know each other were not aware that there's a sort of a way of collaborating together. The other thing, and that comes from the recording, but also in the experience itself, pink noise, or noise in general, masks voice. So it was very difficult for people to communicate because the pink noise was masking them. And then as we were recording, obviously because we were using a fancy GoPro, it was canceling out the noise. And therefore, the recording is not showing the change in the music. We then took that project to our MArch students and brought in a fabrication method. So instead of music, we were trying to figure out how to fabricate sound. Each student figured out a different perspective on the project. One was looking at a phenomenology response of how can you allow or move people through space just by binaural cues and not telling them where the corridor in the space is. And then the other one fabricated essentially 3 different tones that air compressor was passing through in response to the location of the person in the space, trying to navigate them, and then trying to see how people will react to the sound. And so they put essentially a chalk on the floor and encouraging people to fill their shoes with chalk and try to follow the space. So these are the simple sort of small bits of the project. I don't know how much they are computer response, but they are, it's how I kind of see the technologies. That what does it mean? How do people comprehend the sound, the music, or even the images, and what is the quality? What is the importance of the quality of that?
Should start wrapping up.
I'm done.
Okay.
Thank you for having me. So I'm an assistant professor, joined last year in Industrial and Manufacturing System Engineering Department. I'd like to take time back to take you to the journey of my journey to HCI. So everything starts for me as an undergrad in computer science. So I was coding all night long. That's how I learned and gained out experience with the computer part of the human-computer interaction. And then I took a little bit switch in grad school, entering the human factors and ergonomics, like a research area in industrial engineering. So several of my projects is in naturalistic driving data set analysis. We try to analyze human behavior, driving safety, and crash, human errors related topics. That's how I gain experience in the human side. And one of the biggest findings of my entire research area is that is really good, bad posture. Correct your posture as soon as possible, okay? That's really good for your health. Okay, that's a little joke. And then for my dissertation onwards, I want to do something to combine those things together. So that's the interaction part. I started work on driving simulators, so we can program autonomous vehicles' behavior. And we can also to see how human drivers behavior and how to connect those together. So that's the interaction part. So all of these leads to my current lab. So the name is Human-Centered Interactive Autonomy Lab. So in our lab, our goal is try to build customized AI agents that can collaborate as trustworthy teammates with human or human users in safety-critical complex decision-making tasks. Specifically, we want to build theory-driven computational human models, and then they can collaborate with all these computers to avoid intruding or interrupting during the interaction or collaboration. So I'd like to break it down to 3 keywords in that name. So for the human-centered part, so a lot of other studies are trying to treat human as a data generator. What we want to do is to build theory-driven human models. One of the human models we're looking at is the reinforcement learning framework. So it's pretty natural as we learn how to drive, for example, in this case. We don't learn from from that large, thick book of manual. We learn from observations, like observing our parents, observing from the coach in driving school. So that's exactly this flow chart is trying to say. So interact with the environment by observing the state and by doing some actions and to receive some reward. In this case, you are observing the expert's demonstration and you learn those behaviors. And we can use this human behavior modeling to build customized vehicle automation. This is one example that I learned this kind of behavior model from naturalized driving data, and we implemented in color driving simulator, some aggressive behavior and conservative behavior. Also, we can predict a takeover readiness or timeliness in autonomous driving. And more recently, we started a new collaboration with University of Nebraska Medical Center to look at how we can model the older driver's behavior with mild cognitive impairment. And then we can build maybe proactive monitor systems for the driver so we can do something and do some early intervention. And another recent project is we can look at whole body behavioral barometric to look into how we can improve the authentication and a human-computer interaction, their trust, and also some VR security, so in the virtual reality world for human-robot interaction. Okay, and then that's the behavior side, but human has individual difference. None of us can drive the same exactly. So probably from the mathematical model, you need to stay in the middle of the lane, but nobody drives exactly in the middle of the lane. So why does that happen? Because we have different cognition. So that's also the human factors like thinking. We need human mental models. So I'm specifically interested in human trust into all these like algorithms and robots or systems. So we try to build driving simulator studies with different, like for example, here is different transparency. So you can overlay information on the windshield to help the drivers to gain better situational awareness. And then we can induce different dynamics in their trust levels. And we can use some machine learning algorithms to cluster the different people based on their trust toward automation. Somebody like that blue group, they're pretty confident about autonomous vehicles. So they tend to have a high trust level and stay stable even in faulty operations. But some other people are more skeptical in this case. And in this case, we also want to build non-traditional machine learning algorithms. We want to use more theoretical-driven models. We are using the state space model so that you can model the current trust level depend on the previous timestamp's trust level. And then you can also observe some system input. And those are just hidden as in the cognitive states. What you can only observe from the system in that model is the human behavior, either their takeover intent or their driving behavior. So they can be used in our human autonomous vehicles interaction, and we recently explored human-robot interaction in the manufacturing plant. Okay, move to the next keyword, interactive. So for the interaction part, we have the theory-driven human-in-the-loop reinforcement learning algorithm we're trying to build and keep refining. So starting from this human behavior model, and we try to integrate the human trust models into this framework so that when you make decisions, you are not only following the single mathematically optimal solution, like staying in the middle of the lane. You can have some suboptimal actions based on your trust. Okay, that's this flowchart saying. And then we have some interactive test bed. We're trying to collect data and try to validate our methods. So on the left here, we have a simulated manufacturing environment in a VR setting. We also have a very cool pedestrian simulator that you can walk. Instead of teleportation in the VR world, you can actually walk and pick up stuff like in here. So this is our environment, and we have some design tasks for them to do. And we also have a driving simulator, which is a multiplayer platform that will connect the pedestrian simulator with the driving simulator. So you will have this two-angle view. So, and then you can view each other's behavior. And yeah, we can do studies for vulnerable road users. Okay, last one, autonomy. So our lab doing research on autonomous cars, automated guided vehicles, and more recently, we started to look at humanoid robots and quadrupeds, like robotic dogs, how they interact with humans. Okay, lastly, welcome to visit our lab at 1328 Hao Hao, and please sign up for other studies. And if you were asking me to summarize our passion toward HCI, or human-computer interaction, it's right there in the name. We have HCI. Thank you.
My name is Chengde Wu. I'm an associate professor at the Department of Architecture, at the same architecture as Merate. And what I mostly work on building performance and using digital computational tools to simulate and to see how it affects human comfort and things like that. So I'll briefly present three of my projects. One is kinetic facade, the other one is micro-LED facade, and 3D printing that's right outside of the communications building. The first one is kinetic facade. Mostly our building is static, and there are a couple of buildings. We have sporadic examples around the world that moves. And I was interested in how does kinetic facade affects energy consumption and human like a visual comfort in terms of daylight and things like that, depending on which climate you are in, right? Because depending on where you are, the solar angles are all different and things like that. So I selected 16 sites in the United States across the different regions and ran about 70,000 simulations and tried to present the result of it. And this is one of the example, which is a Kiefer Technique showroom in Australia. During the day, they'll move according to the climate elements. And if at night, you'll act as a installation art piece, so it can be interactive with the people. And here is a model built in Rhino, which is a 3D modeling, digital modeling environment, and try to simulate what is the best angle and to preserve energy and things like that. So after about 7,000 simulations, I got the result, which is not so interesting, bar chart. But the results are, typically it works better for hot climate. That is the part of the result of it. And there are some surprises. And even boring numbers. But in the result, I found there are some erratic findings that's not what I expected. So the next step I went to was there are different ways of kinetic facade. You can have folding, you have sliding, you have turning, all that stuff. How that would affect in more broader regions. I pick 2,500 cities globally, try to map it more densely how that happens, and ran about 1 million simulations last summer. It took 2 months of my computer just to run 24/7, and I got about tens of gigabytes of data and waiting for me to process right now. So that's where it is. And on the other hand, I'm working with a couple of undergrad students and two grad students working on building the actual physical prototype and try to use microcontroller sensors to control that and to see how that works. And at some point, try to test out how that affects the energy and also the visual comfort of people staying in the room. So that's mostly where the progress is about this project. And at some point, all the sensor data can be connected to cloud, and then people can use the phone to access the cloud platform and to report their comfort level, and the facade can react to what the people is thinking inside the room. And depending on how many people is inside the room, the temperature could change and all that stuff, and carbon dioxide level could change. You might need more ventilation, all that stuff will respond to the system will respond to the user comfort. And next project is about micro-LED building. This is a bit unique in the sense that we try to apply renewable energy on building facade. So we do a lot solar, wind, and geothermal in buildings. There are a lot of examples to that. But biofuel to building is not very common. And one of the common ways we grow microalgae is in the open pond or in a closed photobioreactors. And we're thinking how to use those kind of photobioreactors on building to generate on-site renewable energy. And we start to do small, like a foot by a foot mock-up, just using 3D printing, just to see how they look, and in terms of different design prototypes. And we start to build a imagining what this could look like in a real building, how the system would work. And I'll just quickly go through that. This is, can I drag it? Looks like it doesn't like dragging. It takes about a minute. I'm going to skip that. So later we built a little bit larger 2x2 feet of a mock-up. It's a little bit functioning, so it's empty inside, so we can hold the microalgae and water inside. And one of this is a smaller tubular algae. That's algae living inside the tubes with the water and nutrients inside, and there's carbon dioxide feeding into that. And from the top, it outputs oxygen as it has a photosynthesis. And on the top of the computer, it's monitoring the carbon dioxide and oxygen levels on the top. And this is imagining how it could go onto a building, actually. And this is a close-up view of that. And we started to, got a grant from NSF and tried to build one of a one-to-one size mock-up. Consider a lot of different manufacturing techniques. Later, we've decided to go with the dual-axis roto casting, and which means that the egg shape is one of the small modules, and it's empty inside. We put liquid resin in it. As it turns, it coats the interior surface of that to make a hollow surface. And typical like a plastic kayak, all that stuff is made of this roto casting technique. And what we learned is that you have two gears that's controlling two different axes. And depending on what the gear ratio is, sometimes you can coat it very badly, sometimes you could coat very a lot better. And this is a 1-to-1 ratio. And what you can notice then, the top surface never face down, and you'll never have a complete shell of it, right? And so we developed a mathematical model to see how you can coat it more efficiently and try to see what the best of the gear ratio is. And we found out the ratio and we tried to build that. This is the planning of how to do that. And later we built one with wood. So what you can see inside at the middle, that is a mold. And we built another with the aluminum. And this side of the image shows that how we start to 3D print the shape and then do a void, a mold, and then casting it, and you have the bioreactors at the end. And we built some custom chambers with Arduino and control the fans and heat all that stuff to cure the resin, and doing some very cheap testing of how the material creep or not, because it's a resin polymer type of material. And also structure testing, like doing some pull-ups and things like that. And at the end, you see there's a big structure. At the end, there's a car jack at the bottom and pulling the assembly at the top, and to see how much of force the joint can withstand. And at the middle, there's a scale to measure that. And the 3D printed joint failed. First, it failed about 400 pounds. The second one endured 600 pounds, which is the maximum of that scale. That's just a 3D printer with our typical polymer printer. And this is the assembly of that. And there's me and my buddy was filling up some of the water and to see if it's watertight or not. At the center, there's some algae filling in. And this one was got the award from Architecture Magazine at 2021. And we started to test how it functions in reality. We built two chambers. One side it mimics climate, the other side mimics the room. And we put the facade at the center and try to test how well it goes. And we test the U factor, which is the thermal performance, and then heat performance and visible light performance. Made some mechanisms and electronic to control the two chambers. And now you see the two chambers, and at the center you see the foam. That's where the facade is, a sample facade to cap in to run the test. The computer is recording the data. And we built a VR model and try to test how people react to this type of building facade. And it was right before the COVID, and then all of the human subject testing was on hold. So that was actually didn't take off. The last project I'll try to briefly go through is the 3D concrete printing. And this is a new technology going on. There are a couple of examples around the world, and someone's also imagining put that onto Mars. Not sure how reasonable that is. And people claim that how much of a labor force a material can reduce, 50%, 80%. And we found so far that's not true, unfortunately. And we have a setting at the CCL building right across the street. It's right about this. You have a mixer, pump, and 3D printer all together. And at that corner, that's what we have, about 12 feet by 12 feet by 12 feet. And that side, we have a larger one. And this is a printer that's erected we're working. I'm working with another HCI professor, Pete Evans. Pete Evans is working on this printer mostly. This is moving right now, and if you go by the CCL, you'll see a small concrete building like this, and that's what we printed with a smaller robot that is about like 6 feet tall, and this arm, you can see that the arms are moving and to try to print that's how that layer by layer is moving up, right? And we stick the up 2 layers to build the building. So in this project, we had the hardware challenges, also software challenges, because it's not uniform. It's not the same as the plastic printer, the software. So we have to make a custom software for slicer and things like that. Also, other challenges like a material, because the 3D printing cannot put fibers in it. So typically it gets a lot more crack easily. So we try to see if we put fibers in how well it can stand. So that's briefly 3 of the project I've been doing. And there's some fun 3D rendering of a Julia set I did.
So we'll take questions for our panelists. I hope this expanded your sense of what HCI can be. Right. So thoughts? Jundi, Merate, or Chengde? Got a red mic.
So Chengde, I got a question for you. I didn't know about the algae. That was awesome. So can you go into a little bit more? So what are the benefits to the building? Like, does it keep the building cool? Are there HVAC? Are there? I mean, I know it's really cool to look at, and obviously, you know, they can consume carbon dioxide. So are there any other benefits to the building that you see as well?
Thermally, it can act as a thermal mass, which means that the outside temperatures are swinging, going to hot and cold like that. And then during its hot days, it's going to absorb that heat. And then when it gets cold, it emits slowly. That's a thermal mass as a buffer. And as a visual things, this can filter out some of the daylight. It can control daylight, and the algae grows as algae gets denser and then filters out a bit more light as it grows denser. And there's a backside mechanism can filter out and to adjust the density of the algae. And of course, there's another way of these oxygen and carbon dioxide. That's another aspect of it.
Other questions?
Thanks for talking. So earlier we heard from 4 alumni who are working in industry. This isn't necessarily about your research, but could the 3 of you talk a little bit about what led you to your careers in academia? Yeah, I wondered if you could talk a little bit about what led you to your career in academia as opposed to industry, since we heard from the industry side earlier.
Well, I mean, for sound, I mean, architects are not really trained to understand sound and to bring that into their designs. And so it's been sort of a fascination for me, mostly because I cannot filter out the sound myself. And I was sort of trained classically. And so it was a bit of a frustration for me that I went through my training, I went through my master's and worked in practice, and it was very difficult. The only way to bring that in is to communicate with acoustic engineers who are kind of disconnected from the idea of design, the architectural side. So then I needed a way to communicate with them, because I was not trained in their language, and they were not responding to what I'm looking for. And then I realized sound is pretty complex, and so then I needed to go into computational design to sort of try to understand how to mitigate that, and then documenting it was very difficult. And so it kind of is there's no specific reason, it just became a journey. I think one of the things that allowed me to move that way is that people think of sound and they're like, oh, it's great, but then no one really understands how that works. Most of the architectural design that we're looking at, or what we're trained in, is to understand the light and what that means spiritually, and if you're building a monastery, or if you're building a classroom or something, but there's no tangible things. And so that became sort of my evil plan, is to sort of understand that and try to bring that into teaching other architects.
Well, for me, one of the reasons is you get a private big office. That's not a lot of job can offer. I saw some smiley faces. You get what I mean. Yeah. So, well, yeah. Seriously. So mainly because that I can experience so many like industries, like in academia. So I have a lot of friends working in tech company because my background is computer science. And they're mainly talking about all the tech, all the big coding related stuff every day. But like last night, we got to hear from Google, we got to hear from like AI in Africa. And we have like people from architect, from design, from all different departments. We can share ideas together. That really opened up my mind. Like, originally, I only working on this kind of human-computer, human-robot interaction, but now I understand more beyond the HCI, like my narrower domain. Yeah, that's definitely something. And then it's definitely working with young people. Like, I really, well, to me, see myself achieve something is not as that enjoyable as like seeing my students achieving something. That my students getting an award, I'm happier than he does. Like, yeah, that's part of the reason. And yeah, thank you.
For me, I was trained as an architect. I did the traditional architecture program, and after I finished school, I had 7 years of practice in architecture firms, so I'm a practitioner at the time. And at some point, I decided to go do a PhD and become a teacher. So I knew that I like teaching a lot, even since I was very young, even teaching my cousins and things like that when I was even before adulthood. When I started is in my undergrad, I grew up in the era of mixture of analog and digital. By that I mean I studied hand drawing and using the T-bars and all that stuff, using pencils, and I learned in class how to sharpen the pencil, use a knife. That's how I did. At the same time, I took AutoCAD class at the time. AutoCAD was the state of the art at the time, right? So you don't have to draw 100 windows, you can just copy and paste. That was an innovation. But at some point, that was not even innovative enough. And during my master's study, my advisor did computational design at Harvard and went back to Korea, and that's where I did my master's at Korea. And I was exposed to different things, and I was really mesmerized by the capacity, what computer can do in terms of design. Right? So that's where I started. I was thinking of, I'm more interested in automated design in a way, so generative design. We don't have to do a lot of, we don't have to copy paste anymore, right? So it's even better. So that's where I started interested in computer, and then came to Texas A&M and did computational design, and that's where I started my academic career. And never regret I step out of the industry because I feel like it's a more energetic environment. I'm always enjoying teaching students and always very happy to see when the students learn new stuff and there's excitement on their face. That's nothing can replace that.
Other questions? Is there time for lunch? Yeah, we have a good time. Yeah.
So I'm glad to see, I'm glad to see all the presentations, but also especially architects who work for Autodesk. So I was wondering if there's anything that actually industry can bring to your research. So yeah, just the other way around. Are there better things that we could be doing in industry to reach to you, and then sort of make a nicer collaboration, and then see the research be part of the software and then software bringing new ideas to research as well?
Money. And overall, I think there's a different spectrum in academia and industry, right? So in academia, when we do research, we try to think more about the theoretic side. And oftentimes when I code, there could be a lot of bugs and I don't cover all the different situations. And just theoretically try to make the framework work. But on the other hand, at industry, that is a real product you have to put out, right? So there could be a synergetic collaboration, so make it a better way of one look at the bigger frame, the other one looking at a more details. So try to make a comprehensive product. Oftentimes, in the past I have a couple of ideas. One of them is building information modeling. That's one we call them BIM-based acoustic simulation, which is a lot easier because acoustic simulation is probably Merate knows really well. It's very difficult to do in architectural field. So if you can do that very quickly, get a rough result, that would be very interesting. But it's my research sort of, I would say it's died because there's no way to catch it up to make a product to the student's hands or someone, the practitioner's hands. I think that's where the collaboration can start.
Others?
Well, I think it's one of the biggest reasons that I went into academia is that billable hours mean that you have to produce something. You don't have time to think, and you don't have time to make errors. And I think however, computational design when I first started, and it was frowned upon. It was considered either voodoo or just waste of time. The client needs something and they want it now. But in the past 5 years, maybe a little longer, there has been a shift. Before that, it was only the bigger offices. They would invest in R&D, and then they would say, okay, this is the thing that we want to produce out of some sort of what we want to have as a signature in our buildings or whatever. So they would invest in that, and they would hire researchers to investigate certain things. But now smaller offices that don't have that money for R&D are actually looking for students and looking for other sort of younger people that know the technology, that are ready to try out different things. And I think open-mindedness from practice and the willing to allow the idea of a new bit of technology to come out, not just as like now AI has become like a big thing for the last 13, 14 months, but at least in computational architecture, machine learning and AI has been around for a while and it's been developing. But it's only now when people that don't do it are seeing the fruit of it. And I think just a little bit of open-mindedness and willingness to try out and hire younger students that are learning these things, knowing that there's going to be good return on that investment.
I'll add an example as well. I had a recent master's student finish, and she was employed at Danfoss, that's manufacturing valves, hydraulics, and we wanted to compare these ergonomic tools that are being touted. So one is from Velocity EHS, and they say, aim your iPhone at somebody who's working, and we will identify their skeletal structure and say if they're doing bad ergonomic things. Well, they make claims they're a great tool, but they're expensive. So we can't really test it against the other tools and validate that. But she's employed Danfoss, which is paid the expensive license, so we were able to do that. So part of her master's thesis is evaluating this tool. Well, that's great. Now I go and contact them again and say, hey, I'd like to use your tool in the future. Don't you want to give me a free academic license? Because it will enable students to use it and get addicted to it and want it later in their jobs. And they're like, no. So, free software is my short answer. Yeah. Yeah. Certainly Autodesk, yes. Other questions? We have time for one or two more. Yeah.
Thank you for sharing. It's cool to see what's new and going on. Of course, I see video game for the different applications. My question would be, do you see like opportunities to use some of the things, the new software in this case, like I'm thinking of Unreal Engine feels like it could really democratize and like lower barriers to do this type of stuff. Like I was watching the State of Unreal presentation, so they're updating like what's possible in the new Unreal Engine updates. And there's some pretty cool like audio ray tracing simulation type stuff, I feel like. Are those things that are like, are you thinking right now like, Chase, I know, we've already done it, it's old, or is there an opportunity to sort of engage people to use those tools, which have like free academic licenses, which Steven gesture, for something like Unreal or Unity? Is that something that we're like doing and looking at, or is that's old hat and it's already been done?
I think that's to you, Merate.
It's not old hat. There's a small barrier where architects are not trained in code. So then you have to bring them up to speed and teach them the fundamentals of like what is an integer, what is a variable, and then bring them up to that. But at the hope is in a few years that they would already be graduating from high school knowing these things, and so then you can jump in and use these engines. But in my teaching, I use processing, and because the students use a lot of Grasshopper, and so there's some C# and Python components that they can build there, but it's mostly scripting. So the hope is yes. By the time they come to us, they already know these things, and then so we can jump into Unreal and Unity, but it takes a few courses before we can get to that.
But if somebody gave you funding to try to make that happen faster, you could probably figure it out, right?
Yes, please.
Other thoughts? Okay.
I just want to quickly tap that on. Sometimes money definitely helps. And in architecture, the students, they just oftentimes don't have the background. Mostly I teach architecture students. So in that case, try to utilize game, and that is a quite big hurdle to start with.
Sylvia, last question.
Thank you. Yeah, we all know that education is not only one way. So I'm wondering, which lessons have you learned from your students that you find more valuable?
Could you elaborate that a little bit more?
Yeah, if you have learned or get some knowledge or maybe experiences from your students that will enrich your classes.
All the time, and sometimes I have something in mind. For example, kinetic facade. I have the theoretical frame. I thought, this is what you can do, and give some examples. And when students come up with some different ideas and something more complex, oh, I've never done that. And there are a lot of different issues I never expected to come up. And then by solving those issues, I learn from those. Right? So that's the student will try something I've never thought about, and then give me challenge. So let me to think about, oh, what is a better way to do this, and learn from it all the time.
Yeah, I agree. So in human-computer interaction especially, so you have so many aspects. You need to work with human, you need to work on computer-related stuff. So by no means I can be an expert in all of those domains. So the students can bring in like new ideas, and they can propose new things. And most importantly, like from human factors perspective, like for me, if I'm thinking about like a experiment procedure or some human behavior, I only have one perspective. But from other person's perspective, maybe that's different, and we can have new or deeper understanding of the cognitive process, how they are driving the behaviors.
Yeah, I think like Chengde and our generation probably learned computer science in a very unconventional way. So each one of us has our own journey because we weren't trained, go to school to do that. At some point, like for example, I had I decided not to become an architect, and I wanted to become a software engineer, and I took a master's, and that didn't work for me. And then open source happened, and I was learning just by investigating online. So when you turn around and try to teach that in a formal way to designers, you cannot follow how computer science does it. You can't follow how engineers do it. But also, it's not an open source thing. It's a classroom. So there's a lot of trial and error of how students respond to different ways of teaching. And also because when you're in studio, there's a different way of, if you're doing like other things that are not computational, there's a different way of learning. And a different design process, and trying to tell them that there's not one way of this process, and trying to allow them to break away from what is tried and true and what will get them the grades that they need requires a lot of testing, and not every student responds the same way.
All right, thank you. Let's thank our panel.